Hi everyone, C4 differential equations then. We've done connected rate of change, which kind of comes under the same guise as differential equations. Remember, it's split into two things, isn't it? It's split into connected rates, and that's where we exploit the chain rule. So that's where we get our, I don't know, volume, change in volume over time, what we want, and then another variable, let's say the radius, as the radius is changing over time, and that could be split even further. We could split that dv by dr into what we want, dv, what we want, dr, and the variable could be the surface area, dA times dr by dt. Do you see? So that's connected rates. We're not solving anything. So when you see the word solve, then it's going to go into this other branch, or find the general solution, or find the particular solution. It goes into this other branch, this separation of variables branch. So this is our forming differential equations and solving differential equations. So what do I mean by differential equation? Well, we've already done a video on forming differential equations, so we know how to form them, and now it's a case of, well, how do we solve them? How do we get them into a form that we can solve them with? And what this is, like I say, is called separation of variables, and we've agreed that a differential equation looks like a gradient function, doesn't it? So if dy by dx equals 3x squared, this is a differential equation. To solve it, we need to integrate both sides with respect to x, and then we have therefore separated the variables, which we'll talk about in a second. Now, therefore, in what form can separation of variables be used? Well, it can be in this form. It can only be used when you have a function of x and a function of y, because that way, if I do it with this 3x squared, you'll see, and then I can use the formula above. So if you can, in other words, if you can split the x and y's up, so if I make this function dy by dx is 3x squared y, clearly there's a function of y and there's a function of x, isn't there? It means that I can get all the x's and y's onto one side. So let's see what I mean by that. So I'm saying if we differentiate the left-hand side with respect to x, we have to differentiate the right-hand side with respect to x. You see? Dx by dx cancel in inverted commas, and you're left with integral dy is integral 3x squared y dx. But we can't integrate this y section because we're only interested in x variables. You see? So can you see we can divide both sides by y, so 1 over y here, and that gets rid of that one, and now you have all the y's on the left and all the x's on the right. Yeah? So in future, what I should do is I should divide by y straight away. So if we do that again, dy by dx is 3x squared y. I divide by y first, so that way I've got all the y's on one side and all the x's on the other side. Then I integrate both sides with respect to x, and therefore the right hand side with respect to x, they cancel, and you're left with what we had before, dy 3x squared dx. And now we can integrate that thing, so we know that's ln y, don't forget your mod, is 3x plus 1 to the power, so that's cubed, divided by 3, plus c. So we get ln y is x cubed plus c. Do you see? And if we want to make this, well, we're going to go further than this in a second with the example, so we'll leave it here. This is what I mean by solving differential equations, getting in the form of y equals. So I could go y equals now, hopefully you're saying it, I need to raise both sides to e, like that, right? We'll talk about that more in a minute. Why do I need boundary conditions, and what do boundary conditions mean? Boundaries conditions, this means like in C1, when you're trying to find a particular solution. Can you see what we found here? I'll write it up here again. So y equals e to the x cubed plus c. Because I've got that plus c in there, that's a constant, isn't it? And therefore, this is called the general solution. So before, in C1, you would get, I don't know, you'd get y equals 2x plus c, let's say, wouldn't you? And then the only way to find that c was if you had a point, because otherwise c could be anything. So that would give you the particular solution, you see? So this is the general solution, because a general solution always has an unknown constant in it, okay? An unknown constant, whereas a particular solution, you would find that value of c, and that's what a boundary condition is then. A boundary condition is a constraint, an initial, it could be called initial condition, i.e. you did an experiment, initially your x was this, and y was this, and therefore you can sub that in and find that unknown, alright? So, if you can see and get your differential equation into that form, into x's and y's, therefore it's separable and you can solve it. So let's take this an example then. So I've got dy by dx equals 1 plus y over 1 minus 2x. Is this in the form of dy by dx is p of x q of y? Yes, it is. It is, because can you see this is 1 plus y, that's a function, 1 over 1 minus 2x. You see? There's my function of y. So there's my q of y, and here's my p of x. So now I can separate them. I need to put all of the y's on that left-hand side. So if I divide, I can only divide, by the way. I can't plus or minus to both sides, because when you integrate, it's not going to work. You're going to have leftover bits. Okay, you'll see that more for yourself if you tried it. So if we integrate both sides with respect to x, like normal, the dx by dx cancel. So you're left with 1 over 1 plus y dy. Whoops, dy. And on the right hand side, we've still got a 1 minus 2x dx. And now we can integrate. So on the left, hopefully we're saying that's ln 1 plus y. Great. Equals, and now ln 1 minus 2x, it looks like a ln, doesn't it, plus c, but should we just quickly differentiate to check, because this is where most problems go, most problems arise. If I differentiate that, that's going to give me 1 minus 2x on the bottom, that's ln f of x, and then on the top minus 2. There isn't a minus 2 here, so we need to times this by minus a half. Be really careful with that. Now, this is fine. This is absolutely fine as a solution, except sometimes it may want stuff in the form of y equals. It looks horrible, doesn't it? How can I put that in? How can I put that in y equals if I've got a plus c here, especially, which isn't in ln form? Well, remember, this is your general solution at the moment, because you have an unknown. So this is a general solution. There's a c in it. C can be any constant, can't it? So what I'm going to do is, if it wants me to put it in the form of y equals, I could just write plus c as plus ln k, because ln of something is a constant and c is a constant. So if I put it as ln k, the reason why I do that is, so if we put this minus a half up as well, so that's ln 1 minus 2x to the power of minus a half, so that's the same as 1 over the square root of that, isn't it? Can you see I can now put all my log rules together? So if I carry on over on the right hand side here, so you can see I've got ln 1 plus y, and on the right hand side, this log plus that log, as you know, they times each other. So now I've got k over 1 minus 2x. You see? And therefore, that's ln, so what's inside there must be the same as what's inside there. So 1 plus y must be what's inside there. And now I can get y by itself. So y must be k, 1 minus 2x minus 1. And this is our general solution, because I haven't got a general point. I haven't got a point to find a specific solution, or a particular solution. Let's go again, but this time we've got boundary conditions. So as soon as you see boundary conditions, or x and y value, or they give you a point, so in this case it'd be 1, 4, you need to be thinking they're giving me that, so I can find my plus c. Alright, so we go again. This time we've got dy by dx equals minus 3 y minus 2 over, and this is going to be a long one, okay? One student once said to me, is this really what they could ask? And you're like, yeah, this would be like a 12-mark question, let's say. Is this in the form of p of x times q of y? Absolutely, you can see that the x's and y's are separated already. My advice, when you've got constants, leave them where they are. So I'm going to leave that minus 3 where it is. So I'm going to put all the y's on the left. So everything to do with y is just in that bracket there. Because remember, I can only multiply and divide. So I get 1 over y minus 2 dy by dx is minus 3 over 2x plus 1 x plus 2. Integrate both sides with respect to x. That cancels that one. Now I can integrate the left, so that's ln mod 1 y minus 2. The right hand side, we've got a fraction. Let's go through our list. Ln, no. Factorize, no. Algebraic long division, no. Reverse chain, no. Partial fraction. So I should have done reverse chain after ln. It's much of a muchness. And now we've got partial fractions. It must be partial fractions. So this is why the students were like, really? You're like, yeah. So quick one of that. Minus 3, 2x plus 1, x plus 2. You guys can do this at the same time if you want to get some practice. Therefore, make the denominators the same. So x plus 2, 2x plus 1. And now the denominators are the same. And therefore, minus 3 must be a x plus 2 and b 2x plus 1. So if we let x be minus 2, you know how to do this. Minus 3, we get b minus 2 times 2, that's minus 3b. So therefore, b must equal 1. And let x be minus a half. Minus 3 equals minus a half plus 2, so that's 3 over 2a. And therefore, a must be minus 2. Yeah? So now, my integral looks like the integral of a over, so minus 2, 2x plus 1, plus b, 1 over x plus 2 dx. And I really should do a quick calculator check on whether that's true, whacking in 0.01. So I would check that my partial fractions was right. So 0.01, put that in there, minus 3, 2 answer plus 1, answer plus 2. What do we get? So we get minus 1.46327, etc. And then if I whack in 0.01 into my partial fractions, minus 2 over 2x plus 1, plus answer 1 over answer plus 2. And I get the same thing. So, it's all good. Discipline. So now we get ln y minus 2 is the same as integral of that thing, ln 2x plus 1, quickly differentiate to check. You'll see that 2 comes out but not minus, so I need a minus there. Be careful. Ln x plus 2 plus c, but because everything else is in ln form, I'm going to go straight to ln k, do you see? And now I can combine my rules, so 2, this goes to ln x plus, so ln x plus 2 times by k, so kx plus 2 all divided by 2x plus 1. And now we got the ln, so y minus 2 must equal k, x plus 2, 2x plus 1. You see? This is still a general solution because we still have an unknown. So y then, yg, is going to be k, x plus 2, 2x plus 1, plus 2. There we go. There's our general solution. 2. But it's given us boundary conditions, so it wants us to find that missing k value. So our boundary solutions, or what I'd like to call initial conditions, so let's always write I dot c, x equals 1, y equals 4. So let's whack that in. Y is 4, k, x is 1 plus 2, 2 lots of 1 plus 1 plus 2. So what do we get? We get 4 take 2 is 2 equals k lots of 3, 3, and therefore k must equal 2. So to finish, our particular solution is going to be yp is 2 lots of x plus 2 over 2x plus 1 plus 2. And it's finished. Finally then, this time we're going back into the forming our own differential equation and solving it, right? So the rate of increase of a population of microorganisms is proportional to the population size. So if we call P the population size, pollution there. Do you reckon that was a Freudian slip between population and pollution? So interesting about our associations, isn't it? So P is population, and we're talking about the rate of increase. So we're saying the rate of increase of our population is proportional to the population itself, and it's increasing, so it's positive, and therefore straight away, as we've said before, that fish sign equals K, so equals KP. Done. Now, given that at time t the population was of size 8, this looks like an initial condition to me, so I'm going to write that down. So I dot c, t is 0, it's telling me the population is 8. And it's also telling me at t equals 1, the population is 56. That's interesting that they're giving me 2 initial conditions. That suggests to me 2 initial conditions must mean I need to find 2 unknowns to find that particular solution. So I'm expecting a plus c, and I've already got a k here. Do you see? Find the size of the population time at time t equals 2. And then the second part, B, says what's wrong with this model. So let's first go from here. We need to solve this, don't we? So is this in the form of a function of P and a function of T? Yes. The function of P is right there, and the function of T is our constant, and we're just going to leave constants where they are. So I put all the P's, basically the top variable, on the left, and everything else can stay. Integrate with respect to t this time, therefore they cancel. This will give me ln p, and now k is a constant, so that's just going to go to kt plus c, isn't it? We still got the plus c. And this brings us to finding p by itself. So this gives us we're going to have to e everything, aren't we, to get rid of that ln. So that's e to the kt plus c. Remember, e all of the left or e all of the right. Now, let's think about this e to the kt plus c. That's the same as e to the kt times e to the c, isn't it, from our log rules, from our indice rules. Now, c is a constant, e is a constant, and therefore e to the c is still a constant. So typically, you'll be asked to put it in this form, where a is your constant, which is e to the c, okay? You're going to be asked to do that all the time. So a is just e to the c. And this is your general solution because you've still got a and you've still got k, which you don't know. And that's where the initial conditions come in, isn't it? That's where these come in. So let's use that first one. So at t equals 0, p equals 8. So therefore a equals a e to the 0, which must just be a. So now we know that a is 8. But this is still a general solution because we still have an unknown constant in it. So now we can say at t equals 1, p equals 56. So 56 equals 8 lots of e to the k because t is 1. 56 divided by 8 is 7. So therefore k is ln 7. Yeah? So now our particular solution, pp, is a, which is 8, e to the k, which is ln 7, all times t. So I write that as 8e to the t ln 7. Okay? Just be careful because otherwise you could read e to the ln 7 times t, which it isn't. So there we go. And the question asks for the population at time t equals 2. So run out of space here if I extend this. So at t equals 2, population is going to be 8e2 ln 7. There we go. 8e2 ln 7. And we get 392. There we go. Fantastic. So that's all of that part A. But what about this part B? What's wrong with this model? And this is what differential equations is all about. I mean, you're trying to model real life situations with equations, and if your equations don't match the reality of what's going on in real life, then your equations are a waste of time. It's crap, isn't it? We are trying to model the world. The world is not trying to model, meet our models, is it? So what's wrong with this model? Well, let's think about it. This is the last bit of this video, so let's think about it. Think about what happens to population sizes and to populations if time goes on forever. Do they just keep getting bigger? Because in our model, p is 8e to the t ln 7. As t gets bigger, an exponential function, so as t gets to infinity, can you see that your population is just going to keep growing? It's going to keep going to infinity as well, which is ridiculous because we'd run out of food, we'd all kill each other for resources. So it's unrealistic model. It's an unrealistic model since populations don't behave that way, whether it's humans, animals, bacteria, whatever. So there we go. Differential equations in a nutshell, separation of variables.